You should see my screen now.
Yeah, and we are seeing the presentation. Thank you.
Perfect. So I'm Sebastian Kreutzer. I'm a PhD student from TU Darmstadt at the Institute for Scientific Computing. And I want to talk about our work on code instrumentation and profiling. And I want to sort of introduce a few different things. First, I want to go into the different tools that are available and that can be used to profile both instrument and profile both OpenFOAM and other scientific codes. And then I want to go into some recent developments we did that also touches the X-ray tool. So our role in the project is we're working part of the work package 5, so code design, profiling, and performance. And here our main task is to provide code instrumentation of OpenFOAM that has low overhead, so low perturbations of the measurements you do, and that are ideally tailored to the measurement objective. And this was used for different aspects in the project. First, it's for general performance profiling and analysis, but then also once you have these low overhead instrumentations, you can do empirical performance modeling where you collect performance data in different configurations and then use that to build a model that can predict scalability issues. And I want to first go into the different tools that are available. So the main tool we're basing our measurements on is SCORP, which is a measurement infrastructure for instrumentation-based profiling and tracing. And in the context of this project, we have developed the CAPI tool, which is short for compiler-assisted performance instrumentation, which is a tool for exactly that, which can be integrated with SCORP and other profiling libraries to sort of get a more tailored instrumentation of the target code. So to give a brief instrumentation and clarify what I mean by code instrumentation. Instrumentation means inserting measurement hooks either by the developer, by the compiler, or some dedicated instrumentation tool. For example, in GCC and Clang, there's this finstrument functions flag, which inserts these measurement hooks at program entry and exit points. At runtime, these hooks then interact with the profiling tool, SCORP or otherwise, and record a trace or also flat call graph profiles. The benefits of using code instrumentation for profiling is that it's explicit. There's no statistical measurements, so you can be sure that everything that is executed is also measured. And we get a direct correlation to source code, which can be difficult when using other methods. However, the main drawback and what we are kind of doing research on is that it can incur higher overheads, which means that the performance characteristics of the program can be changed, or it may just take a very long time to get the profiling data. So you need to find a way to sort of measure what you actually want to measure. So to give a brief introduction on how to apply SCORP to OpenFOAM. So of course you need a SCORP installation, which is available for free. And at the moment you need an adjusted OpenFOAM build configuration that has some WMake configuration files that change the compilation process. And so at the moment you need some special files for that. However, we're working on a simplified wrapper integration and have discussed this with developers, and this should be coming soon to OpenFOAM. But if you want to try it out yourself at the moment, there are configuration files in the repo link below, and these will also be available after the project in the main OpenFOAM GitLab for our work package. So to do measurements with OpenFOAM in SCORP, you can either enable profiling, which means sort of getting a flat call graph profile, and I will show what that means later, or a tracing, which is more involved, and you in the end you get a sort of timeline of all the call events in the whole program, and that's also what extra-E records, this trace. You can also enable connection of hardware performance counters, for example, using the instruction count and cycle count. You can calculate metrics such as the IPC, which can be very useful. So then to get the profile, you just run the solver as usual, and in the end you get a profile that you can analyze. You may have to adjust some variables. For example, scope P has a total memory variable that's quite low by default, and in OpenFOAM usually it's best to just set it to the max value. Okay, so in the profiling mode, we record a call path profile that has sort of an overview of all the function invocations. And this can be analyzed with a tool called Q. There's a command line tool, and also this code that's shown here on the screen. And what we can do here is see the whole call, like dynamic call graph of the execution. We can see different metrics, for example, time, but also if there's hardware performance counters measured, then we can examine them and calculate performance metrics such as the parallel efficiency. It is very useful for hotspot detection and collecting metrics of individual functions. The other mode is the trace mode, and this is similar to what Giuseppe presented. In contrast to the profile mode, here all function invocations are recorded in the timeline, which means a lot more work and so higher overheads and bigger profiling data. And what it can show is all MPI communication between ranks, for example, and all the times for each function invocation. This can be viewed and analyzed, for example, with Vampire, which is a commercial tool, but there are also open source alternatives. But again, you have to be careful with the extent of the instrumentation, because the traces become very large very quickly. So what we have used this sort of landscape of tools is for empirical performance modeling with a tool called extra-P. The idea here is to identify model functions of the runtime of the specific code parts to predict the scalability of these critical regions. So how that works is we do empirical measurements with different different parallel configurations, and based on that the tool fits these measurements to a performance model normal form, which can then help to kind of extrapolate the scalability of each of these functions, and helps to identify if there's a problem in terms of scalability in one of these components. So here on the right, I'm showing some results for the DLR combustor. And you see that the scaling is not great, and you can see it's this LES model here, which is the problem. And if you extrapolate, you can see that this will be the limiting factor. On the other side, if you look on some of the reaction functions responsible for the reaction computation, they seem to be scaling much better. So we can see that this is kind of a problematic function in this case. And it turned out this was the issue that was discussed earlier too, with the wall distance calculation that was inefficient for higher core counts. So I now want to get a little bit more into the overhead management, which I've talked about. As I said, full instrumentations can increase the runtime significantly, and this can be up to more orders of magnitude and skew the results. This effect can be reduced by creating selective instrumentation configurations, which only measure a subset of functions. The sort of common approach to do this is a profile-guided method, where you start out with a full profile or a default filtered profile. And based on this initial measurement, you filter out functions that you observe that might produce high overhead. For example, very small functions like access operators for vector types or something like that with high number of invocations. ScoreP has a semi-automated facility for that called ScoreP Score. And this can generate filter lists using threshold values that you give to it. For example, for the number of invocations, the time per invocation, and the buffer usage. And this file then can be passed to ScoreP when you're measuring, and ScoreP will then not measure these specific functions. You can also use this filter file to apply compile time filtering, where you have a separate build that is only instrumented in the selected regions. Now I'm coming to our developments, which is the more compiler-assisted approach. So instead of doing this profile-guided approach, where you sort of start with a full instrumentation, our idea here is kind of to do a static analysis of the code first, and then decide what we want to measure based on what the user wants, and also on the characteristics of the code. And to this end, we have developed the CAPI tool, short for Compiler Assisted Performance Instrumentation. And this is a tool that implements this compiler-assisted static selection strategy, and also provides runtime library for doing runtime adaptable instrumentation based on LLVM X-ray. What that means is that you can sort of do the same thing that ScoreP can do with the static instrumentation, but you don't have to recompile. So what happens, actually, you have one general instrumented code where the instrumentation hooks are by default turned off, and at runtime we can modify the binary sort of on the fly to activate these hooks and make sure that the selected regions only are recorded. And this is a very flexible approach that also introduces very little overhead if it's inactive. So to kind of illustrate how this works, I have a little graphic here on the right. So you start with the source code, you run some static analysis on the code to get a whole program call graph, and then you take information about what the user wants to measure and put that into our tool, and the tool will produce then hopefully low overhead instrumentation configuration that can be used to run the profiling. I want to give a quick example here. So, for example, one use case is you want to record callbacks that contain MPI communication, and also kernels that can contain loops with a minimum number of floating point operations, but you want to exclude system handlers or inline functions. And with CAPI, you get this DSL where you can specify this. And yeah, this leads to a great reduction of measured functions while still retaining the hotspots in the code. I won't get into the details of the DSL now, but that's sort of the basic idea. And to show some performance results down here. So we have first in this plot the inactive instrumentation, which is just the instrumented binary using this LLVM X-ray approach, but doing no measurements, and there's hardly any overhead at all. Then on the other hand, if you do full instrumentation, you get quite a high overhead of 6x runtime increase. And then we tested some different approaches on how to filter, and all of them produce quite good quite low overheads, and of course you can fine tune them for the application and for the benchmark you're running. So how much time do we have? Okay. Now I want to get into a recent development we've done, and that has to do with improving the trace analysis workflows for MPI-based tracing. So Joseph has presented some of the work that BSC has done using the X-ray MPI tracing tool. And one of the, let's say, limitations of this MPI-based tracing is that it produces less overhead than the full instrumentation, but there's no direct function information directly available. So it's hard to directly map observed issues back to the source code. Call information can be obtained via call stack unwinding, but it can increase this trace size by quite a bit, and also the call stack unwinding depth that is required to find the issue or to find the respective function is unknown a priori. Also, there's still a manual analysis required to find the common caller once you run the trace with unwinding. So what the idea was here is, can we use the static analysis approach to kind of find out from the static call graph which functions may be responsible for a certain region in the trace, and then also can we instrument that region in a trace and generate instrumentation configuration that can be used to analyze this problem, this issue further. So this on the left side here is an example from one of the micro benchmarks that was analyzed by BSC. And at the top here we see there's this region that is outside MPI that shows quite the imbalance between different ranks. But the only thing we see is the beginning MPI call and the end MPI call. And what we want to know as an analyst is the common caller that between these two functions, between the two MPI calls. In this case, manual analysis showed that it was this phase error weight MI calculation function, and we have a call depth of 7 to this MPI weight call on the left side, and call depth of 4 for the MPI Garda call. And now the idea is, given these two direct callers of the surrounding API operations, can we use static source code analysis and static call graph analysis to find these potential callers? And then instrument these callers. So in this illustration on the right, we have the two call traces that lead to the MPI calls X and Y. But in the trace, we only see X and Y. So if we had these the full paths, then it would be easy to decide, okay, B is the common caller, but we don't know this. But if we can find out that B is one of the candidates for this common caller, then we can instrument B and all the call paths below and produce a trace that contains information about the functions in these call paths. The challenge here is to detect and heuristically also filter these candidates for these common callers. So to identify these candidates, we use a post-dominance analysis, and we have discovered that such functions are only relevant if they are common ancestors, which makes sense. And if there's no other node that is on the path between this node V and the two target functions X and Y that post-dominates both of them. So post-domination means that it must be traversed on any path from V to X or Y. So this is kind of illustrated here on the right. We have this static call graph example. And then we do the post-dominator analysis, and we can find out, okay, E and A are potential candidates that could be the lowest common caller for X and Y. However, one problem is that depending on the call graph, if it's very big, like it is for OpenFOAM, then we may have too many candidates to instrument. So what we did is apply a filtering heuristic, and yeah, we kind of prefer candidates that are structurally closer to the target functions. And we measured that by if they have to traverse other candidate functions to kind of get to X and Y. I won't get into too much detail here, but that's the general idea. And we evaluated two flavors. One is a kind of minimal selection that has very low overhead, but may miss the targeted calls for some cases, and a more extended selection at least guarantees partial coverage. But in practice, we've seen that it works quite well. So to show some results, we have evaluated this method both on a proxy app called Lulash and then the much bigger OpenFOAM code. And what we found is that the minimal heuristic was enough for all cases but one, and the extended selection heuristic found all the interesting reasons. Also, compared to the sort of more standard unbinding approach, we had a comparable overhead with the more extended selection, but a lower trace size, and we add more information that is directly available in the trace. So to sort of illustrate how this looks afterwards, we have again the trace that is from the same issue as from the same benchmark in the same region as before, with the MPI states here. And below is the timeline of the recorded functions that we've instrumented. And you can see that you can get quite the detailed information about this region in the trace that's performance critical. Yeah, that's it for me. I'm happy to answer questions.